Welcome back. This is part 2 of non-communicable diseases, and we're going to talk specifically about screening. So remember, screening is the first of our many tools in our public health toolkit for working on non-communicable diseases. We're going to use it for communicable diseases too sometimes, but we're learning about it first here. So screening programs. What are they? So by definition, screening means that you're testing or looking for the presence of a disease or condition in somebody who doesn't have symptoms, right? So this is someone who feels fine. As far as they know, everything's good with them, but you're going to go looking, right? You're going to go looking to see if you can find evidence that there's something brewing, that there's some kind of problem that has started. And with the hope that by finding it before the person even knew it was a problem, you can then intervene earlier and they can have a better outcome. So an example of screening that you all probably have undergone is vision testing, either at your pediatrician's office as part of one of your well child check routine physical exams, or perhaps they did it in your school as well. So little kids, often they don't know that they can't see as well as everybody else. And so we're not going to wait necessarily until they start saying, hey, mom and dad, I can't read the board. We're going to actually go looking for that in advance, because if we can then get them treatment, get them glasses, and then they can see better, they can do better in school, all those types of things. So screening is, by definition, looking for the presence of a disease or a condition in someone who feels fine, who's asymptomatic. They have no symptoms. So screening sounds like a really good idea, and oftentimes it is, but there are some times when screening actually is not helpful. So there's some criteria that we want to fulfill to identify whether screening as an intervention might be effective for any particular condition. One is that the condition has to be relatively common. This is just a feasibility, practicality thing. If it's an exceedingly rare condition and you would have to screen thousands upon thousands upon thousands of people to find one case of it, then it's not going to be very cost effective. It's going to be a lot of hassle, and you're not going to have made much of a difference in the world. Yes, for that one person, but on the community level, you aren't necessarily making any big difference. So you don't want to be spending a lot of time and energy looking for needles in haystacks. You want to look for things that you can find a bunch and make a big difference at that population level. You also don't want to waste your time screening for something that's not very harmful. So for example, actually, I'm going to do an example in a minute. So I'm just going to tell you, you want to screen for something where it's, if you don't find it, something bad could happen to the person. So using the example of vision screening, you know, they might do poorly in school and not realize why, right? Because they're not able to see things well. And then the condition actually is asymptomatic. So the book doesn't say this because it's kind of implied, but obviously if it's something where you would know as soon as you have it, then screening is not going to be necessary. Okay, so let's look at a couple of examples. So the common cold, non-COVID common cold, that's what we're going to talk about here. So is that relatively common? Yes. Oops, oh, we're going to contrast that with breast cancer. Sorry. All right. So is a common cold relatively common? Yes. Is it potentially serious? No. Is it often asymptomatic? Do you have it without realizing that you have it? Not for your typical common cold, no. So that one doesn't meet those criteria. Let's contrast that with breast cancer. Is it relatively common? Actually, it is. It's going to affect anywhere from 1 in 12 to 1 in 8 female-bodied people. Is it potentially serious? Yes, right? It can be fatal. Not always, but often can be without treatment. Is it often symptomatic? Does it often start and you have no idea that it's there? Yes, okay, especially in the early stages. So breast cancer meets those criteria. The common cold does not meet those criteria. So those are criteria that are specific to the condition itself. Now there's going to be some other benchmarks that we want to meet, some other criteria. One is that we have a screening test, a way to screen for the condition that is accurate, feasible, and doesn't pose harm or risk to the individuals. The last one is that finding something earlier actually improves somebody's outcomes. And so we'll see how that's not always the case. Okay, so what we're going to focus on now is how good is the test. So I'm going to focus on that screening test piece. How accurate is the test? And one of the things that I find that the general public tends to not understand or appreciate is that no test is perfect. No medical test is perfect, whether it's a throat swab for strep throat or a blood test for your thyroid or a CT scan to look for lung cancer. No test is perfect. It's going to be wrong some of the time. Now, some tests are really, 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 really good, but none of them are perfect. So that's why oftentimes your doctor or somebody else, you might say, oh, I want to be tested for everything. They might be like, well, actually, not only is that potentially expensive, but it could potentially cause you some harm. So we're going to talk about how we assess how good a test is, right? So if the test is wrong, there are two ways a test could be wrong. One is it could be a false positive, meaning you tested positive. The test says, hey, we think we found the disease, but it's wrong. So you actually don't have the disease or the condition. So that's a false positive. The test result was positive, but it's wrong. It's false. There's a false negative, right? So I could get a COVID test. It could be negative, but maybe I actually do have COVID, right? So it missed that diagnosis. So those are the two types of mistakes that the test can make. So we're going to do something called a 2x2 table. And true confessions, I love these. They're really fun, actually. They're like little puzzles. So let me orient you to what we are seeing. So across the top here, we're going to have disease is present, so people who actually have the condition or disease, and then disease is absent, right? And then on the side, whether their test is positive or whether their test is negative. So what we can see is that if you don't have the disease, but the test says you do, that's a false positive. So you can see how false positive is kind of populated in that box, right? So that's what a false positive would look like on a 2x2 table. The other mistake was where you had the disease and the test said you didn't. The test result was negative, so that's going to be your false negative. So those are the two mistakes. And then, of course, the other two boxes are going to be when the test got it right. So you have the disease and the test says you have the disease. You test positive, that's a true positive. You don't have the disease and the test says you're negative, that's a true negative. So we're going to use this table a whole bunch in the next slides. So make sure you understand this thoroughly before proceeding. If you don't, pause, give yourself a minute. Okay, so here's where the fun starts and we get into some of the math. So when we're looking at how good a test is, we're going to look at two characteristics. The first one is sensitivity. So how good is it at testing positive in the groups of people who have the disease? So how good is it at finding disease when it's there? We call that sensitivity, right? How sensitive is it? Is it able to pick it up and find it? Let's see what this looks like. So here's an example of a test, okay? And so here's my 2x2 table with all the things filled in. So if it's sensitivity, I want to know of all the people who have the disease, which is all the people here, right? How often is the test going to get it right? Okay, so let's say in this example, I have 100 people with a disease. Let me erase that so it's out of our way. Okay, I have 100 people with the disease. If I get a test result that's positive in 98 out of those 100 people, then I would say that the sensitivity, and therefore the other two got a false negative, then I would say that the sensitivity of this test is 98%. Okay, so when disease is present, it finds it 98% of the time. Let's look at example B. So again, my 2x2 table. Again, let's say I have 100 people with disease. And when I use test B, 70 of them test positive, which means I missed 30 of them. So I had 30 false negatives, people with disease who tested negative. So to calculate my sensitivity, it's what percentage of the time was I able to find the disease when it was present? So 70 out of 100. So my sensitivity is going to be 70%, right? How many true positives did I get out of all the people who had the disease? So that's sensitivity. Make sure you've got that one before you continue on. Other test characteristic is specificity. So this is the ability of all those people who don't have the disease to get the right result, to test negative, right? So again, example A, here's my 2x2 table. This time I'm looking at in all the people who don't have the disease, what percentage of the time am I going to get it right? Okay, so again, I'll get rid of that. So let's say I have 900 people who don't have the disease. What percentage of the time are they going to correctly test negative? So in this example, 810 of them tested negative, which means 900 minus 810, there's another 90 people. Oops, what happened there? Oh, I made a mistake. So there should be 90 people in the false positives, right? So I got it right 810 times out of 900. You do the math, that comes out to 90%. So my specificity of that particular test is 90%. All right, let's see how I do with example B and see if I made the mistake with the animations again. All right, so let's look at another example. Here we go. Let's say, again, I have 900 people without disease. I do the test on them. I see what results I get. And this time, 855 of them tested negative. So I did better this time at identifying all of the people, not all, but more of the people who truly didn't have disease. And so my false positives, in this case, there would be 45, which is fewer than before, which should have been 90. All right. So in this case, then I got it right 855 times out of 900 people without disease. So do the math, 95% specificity. Okay. So again, take a moment, make sure you get it, and then we're going to continue on. Oh, there they are. All right, so that tells me how good the test is at picking something up. And so they're going to figure this out in the lab with known samples, right? They're going to have like a vial with the disease agent or whatever, or somebody that they already know for sure has the disease, and then they're going to do an analysis to see how good the test is at picking this up. In the case of an actual patient, though, we don't know if that person has the condition or not. That's why we're testing them out in the real world when we're actually using a test clinically, right? And so in that person, we don't know yet whether they have the disease or not. So now the question becomes, how likely is it that any test result we get is correct? So if I get a positive test result, how likely is it that I actually have the disease? So this is different from what we did before. I'll show you how in a minute. But so if I get a positive COVID test result, for example, how likely is it that I truly have COVID? Or is it a false positive? And if I get a negative result, how likely is it that I truly don't have the disease? So the words we use to describe that are positive predictive value. So if I get a positive test, what's the likelihood that that is an accurate test result and I truly have the disease? Negative predictive value means I tested negative. What's the likelihood that I truly am negative, that I truly do not have the disease? So now we're going to go and calculate these. It's so fun. Okay, here we go. All right. So in order to do this, you need to know two categories of things. You need to know the sensitivity and specificity of the test, and you also need to know what's the likelihood that anybody in the population group that you're testing has the disease. So therefore, you need to know what the prevalence of the disease in the community is. Sometimes we'll refer to this as pre-test probability. So for example, if I said, well, 5% of Stout students currently are infected with COVID. Let's say I had some data where I could say that. Then you would know that with any random person that you tested, there would be a 5% chance that it should be positive, right? So that's the pre-test probability. So before you actually do the test, you can say, well, there's a 5% probability it will be positive. So the prevalence is going to determine the pre-test probability. So in our example here, so this is example A that I did before, where I had 900 people who did not have the disease and 100 people with the disease. That's 1,000 people total. 100 of them have the disease, so 100 out of 1,000 tells me that my prevalence is 10%. Okay, so in that particular example, the prevalence is 10%. You're going to need to know that. So now, let's take a look. Same test, 98% sensitivity. That means I'm going to find 98 of the 100. I'm going to miss 2. My specificity for this hypothetical test was 90%. So therefore, of the people without the disease, I'm going to correctly identify them as negative 90% of the time. So out of 900 people, so 900 times 0.90 is going to give me 810, which means subtracting then, if I got it right 810 times, that means I got it wrong 90 times. So this is all what we did before with sensitivity and specificity. Now we're going to figure out positive predictive value, negative predictive value. So here we go. Out of all of my positives, so if I add 98 and 90 together, I get a total of 188 positives. 98 of them were true. So of all those 188 people, what percentage was the test correct? What percentage of the time was it true? 98 divided by 188 equals 52%. Oh, wow. Look at that, right? So if in that example, if I get a positive test result, the likelihood that I actually have the disease is, well, flip a coin, right? It's like 52%. So does that help me? Well, yeah, I knew before the test that my likelihood was 10% because that was the community prevalence. So now I know my likelihood is higher, but I still don't really know for sure if I actually have it. Ugh. All right, so that's positive predictive value. Let's look at the people who got a negative test, so the negative predictive value. So we had, what happened to my animation? I don't know. Here we go. We had 810 times that we were right, and there were a total of 812 negative test results. So of the 812 people who tested negative, in 810 of them, it was correct. So we're going to divide 810 by 812, and we get 99.8% negative predictive value. Sorry, my head is in the way. So if you got a negative test result, you can be 99.8% sure that you do not have the condition. Right? It's not 100%, it's almost never 100%, but it's really good, right? So that's pretty awesome. So that's how positive predictive value and negative predictive value work, and they're different from sensitivity and specificity. Let's do some more because it's so fun. All right, so here's example B. So again, I have 900 people without the disease, 100 people with the disease, total of 1,000 people, prevalence is 10%, so that's all the same. All right, I'm going to use my other test. It has 70% sensitivity, so I found 70 people to have the disease, right? So I tested positive in 70 out of the 100, which means I missed it or had a false negative in 30, 70 over 30, all right? All right, and I had 95% specificity. So of the 900 people without disease, I'm going to correctly identify 95% of them. So 900 times 0.95, 855 true negatives, which leaves the difference of 45 false positives. Okay, so let's do our positive predictive value. 70 times I was right out of a total of 115 positive test results. So divide 70 by 115, 61% positive predictive value. So you see, this is actually better than the other one, which is interesting. The sensitivity is lower, but the specificity was higher. Look at this. All right, so let's do negative predictive value. So this time, there were 855 true negatives out of a total of 885 negative test results. So divide 855 by 885, you get 96.6% negative predictive value. So this got worse, right? So it's not as accurate as the previous test was for people who tested negative. It's still really good. So if I tested negative, I can be 96.6% sure that I truly don't have the disease or condition. But you can see how, depending on what your sensitivity and your specificity are of your test, your positive predictive value and your negative predictive value are going to change. And so that's one of the things that we need to pay attention to in clinical medicine and in public health when we're trying to evaluate whether a test is going to be accurate enough for our purposes. Let's apply this to something you know. So this is a finding from a recent 2021, but from the summer study, looking at the accuracy of the Binax Now rapid antigen test, which is what they use, at the gym if you've been testing on campus. So they found that the sensitivity, the ability to correctly identify people who have disease, was 91.84%, and the specificity, the ability to correctly identify people who did not have the disease, was 99.95%. So let's, for this example, say that the prevalence of COVID-19 is 5%. Let's say 5% of all the students getting tested are going to have COVID. Here we go. So much fun. All right, so out of 1,000 hypothetical students, then 5% of them have the disease, so that's going to be 50 people, which leaves the other 950 people without the disease, okay? All right, our sensitivity is 91.84. So of those 50 people, I'm going to get a true positive in 91.84% of them, which is going to be 45.92 people. I know, I didn't want to use bigger numbers, so there we go. Which means I'm going to miss it in the rest of those people, which if you subtract out is 4.08. Okay, my specificity of the test is 99.95%. That's amazing. So I'm going to correctly identify 99.95% of 950, which turned out to be 949.53, leaving a difference of 0.47 that I'm not going to correctly identify as negative. They're going to get a false positive. Let's do our positive predicted value. So I got a total of 45.92 correct positive results out of a total of 46.39. So that comes out to 98.99%. So in this example, if there is a 5% prevalence and you get a positive test result on a Binax Now, the likelihood you truly have COVID is 98.99%. Okay, negative predictive value. We got 949.53 true negatives out of a total of, adding the 4.08 false negatives, so all my negative test results of 953.61, so 99.57%. So if you get a negative test result on that swab, the likelihood that you don't have COVID is 99.57%. That's pretty darn good. Now, this is data that was collected using previous variants of COVID. So like the Delta variant was circulating when this particular study was done. So one of the questions that scientists have right now is whether Omicron is going to show up with the same parameters, if we're going to see the same sensitivity and specificity for this test with Omicron as we do with the Delta variant. So far in laboratory studies, it works just as well. There's some anecdotal data, interestingly, which is basically hearsay, that perhaps the Omicron variant infects lower down in your throat more than up in your nose, and that maybe we're missing some of it if we're just swabbing people's noses and not swabbing people's throats. So people are collecting data now to try to figure out what are our test characteristics now that we have a slightly different variant. It's pretty interesting and exciting if you're me. Okay, so that was really, really good when the prevalence was 5%. Let's say that Stout students hardly have any COVID. Let's say the likelihood, the pretest probability of any Stout student testing positive is 0.5%. So we're going to make it 10 times lower now. So let's see what happens to the numbers. Here's my 2x2 table. Again, I'm going to take a group of 1,000 people, and this time 0.5% of them have COVID. That means 5 people out of 1,000. Therefore, 995 people don't have COVID. So here we go. Sensitivity is the same. So out of those 5 people, I'm going to test positive. I'm going to accurately test positive in 91.84% of them, which is 4.59 people. So that leaves the other people, 0.49 people. 41, I got it wrong. False negative. I missed it. Specificity, 99.95. So times 995 people means I'm going to get it right in 994.5 people, right? So I'm going to get it right most of the time. But there's that 0.5 people left over that get a false positive. So here we go with our positive predictive and negative predictive values. Positive predictive value is my true positives over all positive test results. It's going to be 90.18%. That's actually a lot lower. So the other one was like 99 or 98% or something. Now it's a lot lower. So now that if I get a positive test result, there's only a 90% chance I have COVID, which is still really high, but that means there's a 10% chance of my test result being a false positive. Interesting, right? Okay, negative predictive value. So again, true negatives over all negatives, and we're going to get 99.96. That got better, right? So previously it was like 98%. You could be like 98% sure you didn't have COVID. Now it's 99.96%. So isn't that interesting that if the prevalence of the disease goes down, the positive predictive value goes down, and the negative predictive value goes up, right? So you end up having more false positives and fewer false negatives. It's kind of interesting. Let's do one more. So let's say the prevalence of COVID is really high. Let's say it's 25%. And in fact, in the state of Wisconsin right now, of all the COVID tests that are being done, which is not everybody in the state, but of the people who are getting tested, 25% of them are coming back positive. Now, people who choose to get tested are more likely to have symptoms or being in close contact, so they're more likely to have a higher likelihood. But let's just say, for the sake of math, that prevalence of COVID is 25%. Here we go again, total of 1,000 people. So this means 250 people actually have COVID or whatever condition, and well, COVID because we're using the Binax Now data, and 750 people don't. Here we go. There's our sensitivity, so 250 times 0.9184 means I'm going to correctly identify the disease in 229.6 people, which means that in the other 20.4 people, they got a false negative. Specificity. So 750 people don't have COVID in this example. So 750 times 0.9995 means 749.6 of them will test negative, and I will get a false positive in 0.4 people. So our positive predictive value, the likelihood if I get a positive test result that it's correct, right? So my true positives out of all my positives, 99.83. Really, really good, right? So if I test positive, I have it, right? I mean, not always, but the vast majority of the time. Negative predictive value, however, now has fallen, right? So because I've got a bunch of false negatives now because there's just so much more disease out. So when prevalence goes up, our positive predictive value goes up and our negative predictive value goes down because I've got more false negatives and fewer false positives. So isn't that crazy that depending on the prevalence of the disease, same test, same disease, but depending on the prevalence in the population being tested, you're going to get different accuracy of your test result, different positive predictive value and negative predictive value. I think it's fascinating. Hopefully you do too. So in summary, no test is perfect. The characteristics of the test are its sensitivity, ability to correctly find disease when it's present, and its specificity, ability to correctly identify people who don't have the disease. And then we have to take into account the disease prevalence within whichever community or group of people we are going to test in. And then we can use that information to figure out the likelihood that any given test result is going to be correct in an actual patient. That's our positive predictive value or negative predictive value. And those are going to change if any of the above factors change. So here's just some reference definitions and formulas for you as you do some of the activities as part of this unit. I just wanted to make sure you had some reference pages to look at. is the same information, but organized in a different way in case this works better for how your brain learns. So I talked about when is screening effective, and this whole section on sensitivity, specificity, positive predictive value, and negative predictive value was just answering the question of how accurate was the screening test. Okay, so we just spent a lot of time talking about that one little piece. So let's talk about some of the other pieces that we haven't gotten to yet. So is the test feasible and not harmful? So when we're thinking about feasibility of a test, we're talking about how much does it cost? How much of a hassle is it for the patient or for the staff to do it? Do we have systems in place to actually carry it out? Do we have the infrastructure and the supply chains? So right now with the Omicron surge, there are shortages of tests, COVID tests, for example. So it would not be feasible necessarily for our local school district to require every school child to get tested every day before they go to school to make sure they don't have COVID. Right? That's not feasible. We don't have the supply. We don't have the systems in place to do that and to check and to make sure and to run the tests. It's just not feasible, for example. Could it be effective? Yes. Is it feasible? No. Right? And then is there potential harm associated with the screening test? We tend to not think about harm associated with tests, but one is cost. Right? So for example, using the COVID thing, which is not a non-communicable disease, but anyway, COVID tests are often free, but there are other tests that are not. And if you don't have health insurance or if your health insurance won't pay for it, and that's what the Affordable Care Act said they have to, but anyway, cost, it can be a harm to the individual. The other is actual physical harm or medical harm to them as a result of the test. So getting a nasal swab is not a big deal. You might have some discomfort. You could get a bloody nose from it. Usually you're not going to get harmed, but maybe you've had a blood draw where, you know, your arm was really sore for a while, or you had a big bruise or something, or maybe you had a test, maybe you got a blood draw and it got infected somehow, right? So that can always happen. Anytime we do something to a person, there's a risk we could cause them harm. One screening test, for example, is mammography. Mammography is an X-ray of your breast tissue. You're exposing the patient to radiation on purpose, right? So that harm is small, but you want to make sure that any harms that are associated with the test are significantly outweighed by the benefits, right? And then finally, when we're thinking about harm, there's significant potential harm associated with an incorrect result. So a false positive, right? So if I'm told I have breast cancer and I undergo chemotherapy and surgery and all these things, and they go, oh, you know what? Actually, it wasn't cancer after all, right? I just went through all these horrible things, maybe had side effects or complications, which could have been fatal for something that I didn't need. Or if you tell me I don't have a condition and I truly do, say, you know, you do a mammogram and me, and they're like, oh, no, looks clear you don't have breast cancer, but maybe I do, and the test just didn't find it. Well, then there's potential harm because there's delay in diagnosis. And then also, maybe if I develop some weird symptoms in my breast, I might be like, oh, I don't need to go to the doctor. My mammogram was fine. I can just wait and see what happens over the next year. Right? So you could potentially cause me a lot of harm, and I could be worse off than if I had never had the mammogram to begin with. So we really need to think about feasibility and potential harms associated with any screening test. The last question that we need to kind of satisfy is, can early detection improve the outcome? So by finding something earlier before someone has symptoms, are you able to do something different that makes things better? And the answer is sometimes you can and sometimes you can't, and it depends on the condition and what's going on. In the example of breast cancer, for many breast cancers, finding them earlier allows you to get treatment that is more likely to be successful. So finding it earlier, excuse me, is associated in some types of breast cancer with an improved outcome. You're less likely to die from your cancer. You're less likely perhaps to need a total mastectomy for your cancer. But in other types of breast cancer, sometimes it doesn't make a difference. Sometimes that cancer was going to be rapidly fatal anyway, and sometimes that cancer was going to be really indolent or lazy and not kill you anyway, even without treatment. So sometimes yes, sometimes no. So we need to ask ourselves, is finding something earlier going to give us the ability to do something different that's going to make things better for the patient, right? Does this really help? Right? That's what we need to know. And what's interesting is that this is going to change over time, depending on potential new treatments or therapies that are developed, better tests, and as more is learned. So an example of this is, for a while, we thought it would be a really good idea for male-bodied people to do regular testicular self-exams, to examine their testicles and look for any lumps and bumps and things that might indicate that they had testicular cancer. Seemed pretty straightforward, not a harmful test, very feasible. The problem ended up being that the accuracy of that is really low. And so what ended up happening was that a lot of worried male-bodied people ended up coming into the doctor's office convinced that they had cancer. And it turned out that actually they didn't. And then they ended up having, medical appointments and ultrasound tests and sometimes biopsies that they didn't need. The other thing about testicular cancer is that it turns out that the vast majority of the time, it is highly treatable, even if it's already advanced all the way to metastatic cancer. So the thing with testicular cancer is that finding it earlier doesn't make much of a difference at all in terms of your overall outcome. It's usually very highly, highly curable, whether you found it early through screening or you found it later because somebody developed symptoms and they were like, oh, my testicle feels funny, and then went and got it checked out. So this changes over time. So when is screening effective? The criteria we want to satisfy, right? Is it common? Is it a relatively common condition that can be serious and cause negative health problems for people? And is it asymptomatic, right? Otherwise, we don't need to screen because by definition, screening is testing asymptomatic people. We have a good test that's feasible and not harmful, and can finding it earlier improve outcomes? So those are the conditions that we want to satisfy for a screening program. For your activity for this unit, you will apply some of these principles to breast cancer screening with mammography. All right, I'll see you next for part 3.